Okay, so homework 7, we're going to start doing RL circuits and step responses for them. But first we got this pretty simple, basically it's a calculus problem. Now, given IL t for t greater than 0, and we want to find the voltage, well, we want to find the voltage across the inductor. It's going to be the inductance times the derivative of the current with respect to time. So our inductance is 50 microhenry, I believe. Let me check. Yeah, 50 microhenry. So if we take the derivative here, it's going to be a product rule because of this little t right here. So don't just do 18 or negative 180 e to the minus 10t because there's a t in between them. You have to use the product rule. Anyway, so if you do that, you should get 0.9 e to the minus 10t times 1 minus 10t millivolts as your VLT. You could also get 0.0009 volts instead for the, but I chose to keep it in millivolts just to keep it kind of straightforward. Anyway, so now you got to find the power in microwatts of the terminals. So remember, we're just going to use the P equals I times V. We've been using this whole time. So we're just going to multiply our expression we found for the voltage with the current, and then plug in T equals 200 microseconds. So I did the math on paper, and I got, let's see, 16,200, 1 minus 10t, e to the minus 20t. The minus 20t comes from multiplying the two minus 10t's together. You add the exponents. And it's the order of magnitude is microwatts, like the problem asked for. So if I plug in t equals 200 milliseconds or 0.2 seconds, I get a power. Let me do that again. I get a power at 200 microseconds, or milliseconds, not microseconds, of minus 29671 microwatts. Now it's asking if the inductor is absorbing or delivering power. Well, we get a minus sign here, so it is delivering power at that instant in time. This can change as the charges or discharges, basically. So now we want to find the energy in microjoules. We're going to do the same thing, except remember work is going to be power integrated by time. Oops, power integrated by time. Well, if you remember, or not if you don't remember, sorry. I integrated all of it. I ended up getting WT is minus 16,200 over 40, 20t minus 1, e to the minus 20t minus 1 over 20, e to the minus 20t. All this, whole quantity, this is in microjoules. So plugging in t equals 200 milliseconds, I got a work of 222.5 microjoules. The answer I got is negative, but we're asking for it's asking for the energy stored in the inductor. So that's just means it's basically got that much inside. So to find the maximum power, all we have to do is and take the derivative of the power, which we already, maximum energy. You have to take the derivative of the power, or the derivative of the energy. So d work dt, then you get then set that equal to 0. So I ended up just using the power equation because if you take the derivative of this integral, then we ended up getting what we had before, and ended up finding that the maximum was 1415 microjoule, and the time that happened was 50 milliseconds. So yeah, this stuff isn't super hard. I know I didn't write it out all the way, but it's just calculus, so not too bad. Okay, so this one is a little bit similar to the last one, except we have a little bit of a wrinkle here. B1 and B2. Now, I went ahead and solved these because it's quite a lot of work. I'll just tell you what they are and how I got them, and then you can compare your answers if you choose to solve this one. It's kind of lengthy. Anyway, so to find B1, what I did is I used that we're given this information. This is our L, and this is the I0. So basically, I just use that initial condition because whenever t equals 0, sine is 0, so that means the B2 term goes away, and you can solve for B1 by itself. And then, once you have B1, plug it back in for B2 because we have a voltage right here. So we're going to integrate we're going to integrate the current and plug in the voltage initial value at time equals 0 and use that to find out what B equals 2 or B2 is. So once you have those two values, sorry, we got to take the expressions we've derived for the voltage. This is something you get as part of the process, basically. So 4.25, that's our initial voltage, cosine 200t minus sine 200t. And that's from the derivatives, basically. That's where that's coming from. Anyway, e to the minus 50t. And then multiply them together. Power t is going to be VLT times ILT. You get an expression that should look something like this. It's kind of long. 4.25 cosine 200t minus sine 200t, not 20t, 200t. This whole thing, and then 0.075 cosine 200t plus 0.125 sine 200t, and then the exponent e to the minus 100t. It's just, once again, exponent rule, 50 plus 50, or rather 50 minus 50. Anyway, or minus 50 minus 50. So now if you plug in 25 milliseconds at that time, value I calculated was minus 42.7 milliwatts, which obviously means that it is delivering power at that instant. So yeah, a lot of the trickery in this problem is finding these B1 and B2 terms, and since it's not really a math class, I don't think it's worth showing you how to do all of that. 6.23, is going to be kind of like those older resistor problems where you added them up in series and divided them down in parallel. Now, inductors follow the same kind of rules, so we're going to use that to find, or those two rules to find out the equivalent inductance with respect to these two terminals A and B. Now that's pretty simple. One thing that may be a little bit confusing, these are in millihenry, which is 1,000th of a henry. But since they're all the same order of magnitude, we can just ignore that for now and put it in at the end. Now, first thing I'm going to do is realize, okay, these two are in parallel with each other. The 30 millihenry and the 15 millihenry are in parallel. So 30 in parallel with 15 is 10, and that new 10 is in series with that original 10, and 10 plus 10 is 20. So now we have an equivalent inductor, 20 millihenry in parallel with that 20. Now 20 in parallel with 20 is going to be 10. So now we've got kind of an equivalent inductor. We ignore this. Say that equivalent inductor is 10 millihenry. Now I'm going to go ahead and simplify the other ones quickly. Now these two, the 12 and the 24, are clearly in parallel. 12 in parallel with 24 is going to be 8. And that new 8, say that new 8 is in series with the 10. So 10 plus 8 is 18. Then that new 18 is in parallel with the 9. And 18 in parallel with 9 is 6. And then finally we have 6 in series with 8. And that's going to be 14 millihenry. Now I went a little bit quickly. It may be helpful for you guys if you do them step by step, these simplifications. But I have a lot of practice doing this, so I can do it basically in my head. Now I'll move on to the next one real quick. So we're going to follow up the last one using the exact same kind of process. Now this one is a little bit more forgiving. Let me scroll up a little bit. A little bit more forgiving. It's also a little bit more confusing, I guess, because there's this parallel common node over here. But we'll get to that in a moment. Anyway, these two are in series, the 18 and the 12, so 18 plus 12 equals 30. Now, that new 30 is in parallel with that 20. So 20 in parallel with 30 is, let's see, 12. So we have a new 12 that is in series with the 38. So 12 plus 38 equals 50. And that 50 is in parallel with the 75. 50 in parallel with 75 is 30. So I'm going to go ahead and sort of like simplify this whole network, cross out all these basically, and say we have a new L right here that is 30. So now you can see, hopefully, that the 30s are in parallel with each other. So 30 in parallel with 30 is 15. That new 15 ends up being in series with the other 15. Now 15 plus 15 equals 30. Once again, we've got 30 microhenry. Sort of, let me write it in here. Say that then equivalent L. So we have it's 30. So 30 in parallel with the 60 is going to be 20. And finally, we're left with that whole equivalent. Oops, let me actually erase that. Come on. Okay, my eraser doesn't want to cooperate, but just pretend that I erased it and I drew in something like this. This is the 25, and this is the 20 we just calculated. So they're in series. 20 plus 25 equals 45. So the equivalent inductance is 45 microhenry from A to B in this circuit. So these two parallel inductors are connected across the terminals of a black box right here at time equals 0. Now we're given a function for the voltage with respect to time. So say this is a VLT for both of these inductors. And we're also given the initial currents. So initial current through these two, 4 amps and 2 amps respectively. Now, first step is we want to find the equivalent inductor for these two inductors. And we're going to use the rules that we did in the last problem. So 3 in parallel with 6 is going to be 2 Henry. We're also going to need to find out what the sort of IL total for the equivalent inductor would be at 0. So that's going to be, if you add them up, IL0, 1, or I1, 0, and I2, 0, which ends up being 6. So we're going to need that sort of initial condition later. And remember that. And now we're going to find out what the current is for the equivalent inductor. Now, the voltage was given as, well, let me write this out first. So LEQ V dt. I should say V T dt, but it doesn't necessarily have to be a function of time. But in this case, it is. So ILT is going to be 1 over RL equivalent, which is 2, and then 12 e to the minus t dt. Now we're doing an indefinite integral, or the antiderivative, so don't get confused. The only reason we're doing that is because we're trying to find the total behavior, so to speak. So anyway, if we move this outside, this is going to simplify to minus 1/6. But we'll worry about that in a moment. Or sorry, not 1/6. It's going to be 6. That's going to be minus 6 out front. And the antiderivative of e to the minus t, as we all know, is going to be e to the minus t over 1 minus 1. So if we combine the minuses, then we get a plus. So ILT for the equivalent inductor is going to be 6 e to the minus t plus c, or our arbitrary constant. I'll call that C0. Now, we're given the initial, or rather we calculated the initial current for our equivalent inductor. So if you set t equal to 0, this is going to go to become 1. So we say that IL0 equals 6 plus C0. Well, if we know that IL0 equals 6 already, that means that C0 equals 0. So our total expression is just like that. So we're going to do the same kind of process to find I1t and I2t. I1t is going to be minus 1 over the equivalent inductance, which is 3. Double check, I'm pretty sure it's 3. Yeah, 3. 3, and then there's 12 e to the minus t dt. So 4 divided by 3 is 4. 12 divided by 3 is 4. So minus 4, and then minus 1 e to the minus t plus c. I'll just keep this outside. Plus plus. I'll call this c1. So that's going to be I1 t. I should actually not have the pull out the 4 because it's, let me just get it like this. That's mathematically correct. Anyway, so if we know that I1 of 0 equals 4 amps, set this equal to 0, end up with, wait, is it I1 or I2? I wrote them down wrong, my bad. If you caught that, that's just not being careful. Anyway, so I1 0 is known to be 2 amps. So if the expression for I1 0 is 4, let me actually, yeah, that's 1. Is 4 plus C1 equals 2. That means that C1 has to equal negative 2. So the expression for the current is going to be 4 e to the minus t plus C1, which is minus 2. So let me go ahead and box that up so I don't get it mixed up with the other ones. Oh, and I should also write the unit. These are amps. So we're going to do that same process again for I2t. 1 over the equivalent inductance, which is 6. I'll go ahead and pull the 12 out already because you know the drill. And the antiderivative, e minus t plus c2. All right. So this thing's going to simplify to, let me just write it out. So 12 divided by 6 is 2. Minus minus are going to cancel. 2 e to minus t plus c2. That is I2t. Now I2 0 is known to be 4 amps. So if we plug in 4 equals 2 e to the minus 0 plus c2, this goes to 1. That means that c2 has to equal 2. And I2, come on. Please don't stop writing eraser. Okay. I2t is going to be 2 e to the minus t plus c2, which is 2 in amperes. So that's the first two part of the problem, or first two parts of this problem. First three, I should say. So now we want to find how much energy was delivered into the black box. Well, to do that, we're going to need to know the power, and then we can integrate the power with respect to time. We'll find the work. So I'll just do P equals I times V. Sorry. PT equals ILT times VLT. Now this is why I went ahead and calculated that expression earlier for ILT. Anyway, that means that here's our V e to the minus t times our IL for the equivalent inductor. It's going to be 18 and then e to the minus 2t, or sorry, not 18. I did addition in my head for both of them. It's going to be 72 e to the minus t watts. So if we integrate this, we can find the work. So 72, and we're going to integrate from times 0 to infinity, e to the minus 2t dt, which is going to be 72 over minus 2, and then e to the minus 2t, infinity 0. At infinity, it's going to tend to 0, and at 0, it's going to become 1. So let's see. This is minus 36, and then it's 0 minus 1, so 36 joules. So that's how much is in the inductors. It's, yeah, how much is initially stored in the parallel inductors. I'm sorry. They're a little, I did this out of order. How much energy is trapped in the ideal inductors? That's the 36. Anyway, so now that we know how much the inductors have, we're also going to find out how much the box is delivered. So to find the initial, we're going to do 1/2 of each inductor. Let me just say LEQ, I guess. And then the initial current 0, or the initial current squared. So that's going to be the, let me actually write it in just to say that this is, let's do I1. So L1 is the 6, I believe. That's the 3. Okay, so 3. And we're going to add them both up. I2, 0 squared. That's going to be 1/2 times, let me just write 3/2. 3/2, and then I1 is 4, 2. So 2 squared plus 3/2, which is 3, and 4 squared. So let's see, 6 plus, that's 54 joules. Okay, so if we want to find out how much is delivered to the box, we're going to do 54 joules minus 36 joules equals 18 joules. So that's how much the box got. Yeah, so all this is just calculus stuff for the most part, finding the solution to basic differential equations. So this is our first real circuit analysis problem with inductors. Always one thing we want to keep in mind as we go forward. Tau is L over R in these circuits. It's not like RC. It's not R times L equals tau. It's L over R. And also, the reciprocal is going to be R over L. And that'll become important, or that'll see why that's important later. Anyway, since the inductor and the resistor are in series, the current through them is the same. So that's where I got this expression right here for IL. It's just the voltage drop across the resistor divided by the resistance. Anyway, I'm going to go ahead and put them in parallel just to make calculating the voltage a little bit easier. 40 in parallel with 10 is 8 ohms. So I'm going to set those equal to each other. So 240 minus V1 over 16 is V1 over 8. And you can see that since these are the same kind of, I want to say the same base, then you can see why making it 8 makes the math a little bit simpler. Anyway, so I'm going to multiply everything by 16, 240 minus V1 equals 2V1, which means that V1 equals 240 divided by 3, which is 80 volts. Which means that IL, make sure that's in there, IL0 minus equals 80 divided by 10, which is 8 amps. So since we know the current can't change instantaneously, because it would require infinite energy basically, then IL0 is going to be 8 amps too. So now we got to do something a little bit strange, you might think, to find out what the initial voltage across the inductor is, because we're solving for the voltage, not the current. So VL0 minus is going to be, or I should say VL0 is going to be IL0 times REQ, I'll call this REQ prime, because I have another R equivalent in this circuit, or in this problem. Now how are we going to calculate REQ prime? Well, I have a little network over here. And the reason why I drew it like this is because the inductor, this is after, or this is not after, this is just before the switch is thrown. And basically what I did, I shorted out the voltage source because ideal voltage sources have 0 internal resistance. And I left the resistor out because at the steady state, the inductor basically behaves like a short circuit, right? So we need to, in order for there to be a voltage, we need to have something to compare that current against, basically. So to find VL0, we're going to find the equivalent resistance and multiply it by that. I hope it's not too confusing, but once again, REQ prime is going to be 40 in parallel with 4 plus 6, which is 10. So that's 40 in parallel with 10, which we already calculated before, is 8. So that means that VL0 is IL0, which is 8 amps, times 8 ohms, or 64 volts. Now another thing, the voltage across the inductor here is considered negative compared to the ground. It's not super important. I'm just going to say that the magnitude is 64 volts. Anyway, that's our VL0 we're going to need later to solve the differential equation. Now I'm going to find the REQ after the switch is thrown. So basically, this is after the switch is thrown and the voltage source and everything become disconnected. They share the same ground, but there's no connection here anymore. Basically, I want to find another equivalent resistance. This is the true, I guess you could say, equivalent resistance. And the way we're going to do that is we're going to take out the inductor and see what it looks like to be the inductor in this circuit. So these two are in series. That's going to be 10. So it looks like 10 in parallel with 40 plus 10. We determined this as 8 before, so this becomes 18. So our equivalent is 18 ohms. And we're going to plug that in over here. And we're going to finally solve for VLT. So I'm going to write ILT in a different form, same form actually. I'm just going to simplify it. So VLT 0 minus VLT is negative VLT over R equivalent, which is 18. And now I'm going to take ILT and substitute it in to this expression. So we get VLT equals 72 E minus 3 D, let me put this in the brackets, VLT over 18 dt. So one thing I'm going to do before we do anything else, I'm going to use basically some rules of differentiation. I'm going to pull the minus out and put it in front. So let me actually draw that again. I'm going to pull the minus out, put it in front. I'm going to do the same thing with the over 18. So it'll be negative 1 over 18, basically. And the reason why we're doing that is because I want to move the negative d VLT dt to the other side and get it in our standard form. So I'm going to do that. I'm just going to add it to the side. Actually, let me put this here first. Over 18 and dVLT dt plus VLT equals 0. So you may notice that this is tau, because this is L and this is R equivalent. So let's go ahead and calculate that real quickly. 72 divided by t, I get 0.004, which is also 1 over 250. So I'm going to divide all these entire expression by tau, which we just calculated as 1 over 250. And that would, if you did it straight up, it would just be 250 VL right here, and then this would go to 1. But I'm going to keep it as a fraction because it'll make sure that we're in our standard form as we want to make our lives easier. So dVL dt plus VLT divided by tau, which is 1 over 250, equals 0. Alright, so we know VL0, we calculated it as 64 volts. We need to know VL infinity. We can calculate it using K and tau. That's K. As before, that's tau. So 0 times anything is 0. And we have everything we need to find out what the voltage respect to time, or how the voltage of this inductor, across this inductor I should say, changes with time. So V infinity is 0, so 0 plus 64 minus 0 times e to the minus t over tau, so that's going to be minus 250 t volts. There you go. It's not too bad. The most tricky part, I would have to say, is finding out what VL0 is. Because this is kind of unintuitive, in my opinion, to sort of substitute the rest of the circuit to find a voltage. But we're trying to basically find out how much of a drop there is with this 8 amp current pulled out of the expression. So time to move on to the next one. This problem is a little bit different, but also kind of similar to the last one. The one quirk is that we have this dependent source, so we're going to have to make sort of a Thevenin equivalent sort of way of finding the equivalent resistance for that, because we don't have just resistor, but it's not too bad in this problem. The first thing we're going to need to do, though, is find the initial condition for this. Now, at the steady state, once the inductor is magnetically saturated and everything, this it'll become basically a short. It won't be pushing back against the current anymore because it's been stabilized. So at a steady state, it basically is a short, and short has zero resistance, or an ideal short has zero resistance. So it's going to get all of the current. This is going to get none of the current, and also there's no voltage drop across this resistor. So that means that the dependent source right here is open. It's not providing any current. So we can surmise that IL0 minus is 4 amps. It also is going to be IL0 plus after the switch, and right when at the instant the switch is thrown, because the current cannot change instantaneously, because we need infinite energy to do that, and we don't have that. So to find the equivalent resistance, we need to find our RC time, or RL time constant. We're going to build an equivalent circuit sort of thing. We're going to break out this, and we're going to attach a test source. Now I chose 1 volt. It doesn't matter, but if VO is 1 volt, and it means that the current I is 4 times VO, so that's 4 amps. And if you take the 1 volt source, divide it by the 4 amp current, that means the resistance is 1/4 ohm, 1/4. So if we want to find VL0, the voltage, the initial voltage of the inductor, which we'll need for calculating the final voltage, or rather the equation that gives both of them, we're going to need the equivalent resistance, which we just calculated, and the initial current, which we already calculated just before this. So 0.25 ohms times 4 amps equals 1 volt. So VL0 minus and VL0 is 1 volt. Now we're going to take the equivalent resistance we plugged in, and we're going to find the transient state, the transient behavior of the circuit. So it's, this is 1/4. So I'm going to redraw it. I'll rewrite it as not blue. There we go. VLT. And it's going to be, I'll leave it in a fraction for now, but it can also be minus 4 VLT. Well, there's no harm in putting it up front. Let's make it minus 4 VLT. Alright, so if we have this expression for the current and this expression for the current, I'm just going to plug that in and solve the differential equation. So VLT equals 5 millihenry. I'm going to pull out the -4 from the derivative. So we're just going to have dVLT dt. I'm going to move to the other side. So we have, what's 4 times 5 minus 3? So that's 0.02, I think. I'll check it in a minute. That sounds right. 0.02 and then dVL dt plus VLT equals 0. We're going to bring it into our standard form. I'm going to divide everything by the 0.02, which turns out to be the RL time constant. Oops. That's not a coincidence. That's just what the definition is. So that turns out to be 1/50, but we won't worry about that just yet. Anyway, so now we're in our standard form. Let's go ahead and calculate V infinity. It's going to be K times tau, and K is 0, so that's 0. VL 0, we calculated as 1 volt. So our expression for the voltage, across the inductor is going to be VL infinity, which is 0, plus VL 0 minus VL infinity, which is 0, times e to the minus t over tau. And t over tau is 150, or it's 1 divided by 50, so it just becomes 50 t, and that's volts. So yeah, it's not too bad. The only tricky part, I'd say, is that, once again, like the last problem, we had to find the initial voltage using the equivalent resistance seen by the inductor at that state with that current. So this problem's a little bit different than the last one. We're going to use the same kind of rules for the physics of inductors, of course, but we're going to consider just the currents, not the voltages. So we're not going to need to solve a differential equation. In fact, it wouldn't be possible to do it using that given thing right here, because there are two inductors right here, and we can't simplify them into one inductor that is equivalent to them in terms of its behavior. We could if, say, there was a wire between here and there, but there isn't. So they're not in parallel. Anyway, so the reason why we can't do that using that is because it would make it a second order differential equation. The inductors would be affecting each other throughout their discharge cycle, so they're going to change the voltages. But the currents are largely unaffected. So what we're going to do is we're going to find out the steady state conditions. We're going to use that to find the initial value of the current and the final value of the current AB. I should actually mention the current AB is whenever the short is made at time equals 0, that is the current AB. And we're going to use Kirchhoff's laws and the behavior of the inductors to determine that. So the first thing we need to do is find out the initial sort of state for the inductors before they discharge inadvertently, as the problem says. Now, at the steady state, they act like short circuits for the reason I've mentioned a couple times now. And we're going to, sorry about that, we're going to solve for the V1, and that's going to be our VL0, so to speak. And we'll see why that's useful in a moment. Anyway, so 165 minus V1 over 5 equals V1 over 5 plus V1 over 3. Now I'm going to multiply everything here by 15 to get rid of all that business. Let's see, 165 times 3, 495. I need to mute my phone, sorry. Minus 3V1. Oh, the denominator goes away, sorry. Equals 3V1 plus 5V1. So that means that, move the 3 to the other side, 11 So V1 equals 495 divided by 11, which is 45. So the initial voltage is going to be 45. Now we're going to use that information to determine what happens after that an inverted switch. No, it's not really a switch. The inverted short happens. So I'm going to go ahead and write in what our V1 0 minus was, 45 volts. We're going to go ahead and consider each inductor in its own little box, so to speak. Consider its behavior independently. So I'll put this one in green and this one in blue to make it clear what I'm doing the two different ones. So the first thing we're going to do, one thing I should mention, once this short is made, as far as the inductors are concerned, none of this stuff is here anymore. They just see that short and they want to send current through it. So this business over here doesn't affect this behavior of these anymore because they're sort of outside of the circuit. Anyway, so I'm going to start, let's find the sort of the IS. So finding IS is easy because it's just a resistor and a voltage source. So IS is going to be 165 volts divided by 5 ohms, which is 33 amps. Oh, I should also mention, if you do Kirchhoff's law, circuit law, that's your expression for the currents. I went ahead, since we're solving for IAB, I went ahead and moved the two inductor currents to the other side, and we'll consider them later. Anyway, so to find the inductor currents, I'm going to do this one in blue for I1. We're going to use our little expression here. So I1 T is going to be 45 volts divided by 5 ohms times e to the minus t over tau. Now tau for this one is going to be r over L, as with we had, L over R. L is 12.5 millihenry, and R is 5. So 12.5 millihenry divided by 5. I get a time constant of 0.0025 seconds, which is 1 over 400. So this is going to be 1 over 400. So that means that I1T is 45 divided by 5, which is 9 amps, e to the minus 400t. I'll go ahead and write it there. I hope that's not hard to read. It's a different color. I apologize if it is. I just try to keep it clear what I'm doing. So I'm going to do the same thing for I2T. We're going to have that initial voltage divided by R, then e to the minus t over tau, and tau is going to be, once again, L over R, 3.5 millihenry divided by 3 ohms, which is 3.5 minus 3 divided by 3. Not a pretty number. Did I write the question down right? 3.75. Okay. Good thing I checked that. Because the number I was getting was not pretty. So pretend that I didn't make that mistake. I'm sure you guys are all yelling at the screen right now. Made a mistake. Okay. So 3.75 minus 3 This is going to be 1.25 e minus 3. So 0.00125. I believe that's 1 over 800. Yeah. So that's 1 over 800. So 45 divided by 3, that is 15. E to the minus 800t amps. Let me go ahead and circle the other one too, just so I don't forget about it. So if we want to find out what the current IAB is, we can make that expression using Kirchhoff's circuit law, or Kirchhoff's current law. So IABT is going to be the IS, which is a constant, minus I1T minus, well, I'll just go ahead and, we already wrote that up there, so I'll write in the expressions we calculated. So 33 amps minus 9 amps e to the minus 400t minus 15 amps e to the minus 800t. I'm going to put the unit here. Okay, so I believe the question asks for the initial state. So let me scroll up and check. Problem asks for the initial current. Yeah, the initial value of the short circuit current. So all we have to do is set all of this equal to 0, or set all the t's equal 0. So 33 minus e to the 0 is 9, because e to the 0 is 1, minus 15, same thing as before, equals 33 minus 15 minus 9. Unless I did a mistake, that is 9 amps. So that is the initial current. And we want to find the final current. We're going to put in IAB infinity. So what happens to e to the minus whatever as it tends to infinity? It goes to 0. So 33 minus 0 equals 33 amps. Not 3, 33. All right. So now we have to find, I think, 19. Yeah. How many microseconds after the short circuit has occurred is the current in the short equal to 19 amps? Well, to do that, we're just going to set IAB to equal 19, and we're going to solve for t. So 33 minus 9 e to the minus 400t minus 15 e to the minus 800t. Now, this one is not the prettiest expression, but if we want to find out what this whole expression is, there's a couple ways to do it. I think that the easiest would probably be to use a calculator, but we can also use some logarithm rules. So if we take the 14, or not the 14, if we take the 33 minus 19, or yeah, 33 minus 19, that's going to be 14, and then e to the minus, or sorry, 9 e to the minus 400. All right, so this one, I couldn't figure out how to solve this by hand, so I went ahead and used Wolfram Alpha to calculate it. And the time where that occurs is approximately 850.6 microseconds. Now, that basically means that at this instant in time, these inductors are their total current, so to speak, that's flowing through them is equal to 14 amps, because 33 minus 14 is 19. So there you go. Maybe a little unsatisfying to have a computer solve that last one, but it's a nasty sort of equation with exponents, and you can't really solve it directly without making approximations along the way, and I don't know how to do that. This problem is a little bit different than the other one, where we have to find IOT and VOT. IOT is this current, and VOT is this voltage, as described in the diagram. And when we get to finding IOT, we're going to use the same kind of trick, kind of like the shortcut that Reza shows you guys. Though we're going to find it using that sort of shortcut, and then we're going to use the definition for the voltage across the inductor and the equation for resistor. Use that to find out VOT. So to do that, the first step is we need to find the initial current in the inductor, and to do that we need to find the initial voltage at V0. So it's not too bad. It's the thing we've been doing this whole time. 800 minus VO over 120 is going to equal I1, which is VO over 40, plus VO over 10. So multiply everything by 120. You're going to get 800 minus VO equals 3 VO plus 12 VO. So that means that VO equals 800 divided by 16, which is 50. Which means that IL0 is 50 over 10, or 5 amps. So I'm going to remember that later. That's going to be IL0. Now we're going to consider, after the switch is thrown, we're going to find the equivalent resistance seen by the inductor. So we have 10 ohms in series with 8 ohms, that is in parallel with 40 ohms. So let's see, 8, I already did this calculation, so 16.67 ohms is the R equivalent. We're going to need that to find the time constant. And now we're going to consider the currents and voltages throughout the circuit. Now, we've got two of the three things we need for finding IOT. We've got the R equivalent for finding the time constant. We also have the initial current. So now we need to find the final current. Then we'll use these equations to find out what IOT, or rather what VOT is. So I'm going to go ahead and think about what happens as the circuit reaches a steady state. Well, just like it did in the beginning, the inductor is going to eventually settle down and act like a short once it runs out of back EMF basically. It can't push back anymore. So there's not going to be a voltage drop across it other than the parasitic resistance, which we don't account for in these calculations. So we're just going to go ahead and find the final current using the same technique that we did to find the initial current, pretty much. Equals 50. So to cancel out the denominator, since this is like 10/3, if we multiply everything here by 3, then we'll get, I'll multiply everything by 60 just to keep the numbers clean. So I'll multiply everything here by 60, so that's going to become, let's see, 60 divided by 6.67 is approximately 9, so if you include all the digits, it'll be 9 VO plus 6 VO equals 3,000. So 3,000 divided by 15 will be VO. So 3,000 divided by 15 is 200 volts. So that means that IO infinity is 200 divided by 10, or 20 amps. I'm going to go ahead and write it in IO infinity. Okay, so we have IO 0, which was 5 amps. We have IO infinity, which was 20 amps. Oops. Let me redraw that. 20 amps. And we have our equivalent, which was 16.67 ohms. That means tau is going to be L over R. So L is 40 millihenry divided by 16.67 ohm. So 40 minus 3 divided by 50 divided by 3 is 2.4 milliseconds. Okay. So if we want to find the current expression, we're just going to use something similar to what we do with the voltages. So I'm going to go ahead and write it out. IOT equals the infinity current, so 20, plus, let's see, 5 minus 20, e to the minus t over tau, which is 20 minus 15 e to the minus 416.67 t. Okay, so we have an expression for IOT for time greater than 0. We're going to use that to find out VOT. So to do that, we're going to go back to our equations. I'm going to go ahead and copy these real quick. That's what we need. Come on. Oh, there it is. Come on. Sometimes OneNote doesn't like me. There we go. So, to find the VOT, we're going to take, let me go ahead and just draw an arrow. I'm going to take this expression and multiply by 10. So 10 IOT equals, or sorry, plus VLT equals VOT. So if we can find VOT or VLT, then we can find VOT pretty easily. So 10 IoT is going to be 200 minus 150 e to the minus, I'll just leave it as t over tau, just so I don't have to write that out again, t over tau. And then VLT is going to be 40 millihenry times the derivative of 20 minus 15 e to the minus t over tau with respect to t. So let's see, the derivative of that's going to be, is going to be 0 because constant, and the derivative of that's going to be minus 15 times t, so it's going to become plus. Okay. So final expression, let's see, 200 minus 150 e to the minus 41667 t plus 40 e minus 3 times 15 times 416. Oh wait, tau is oh no, it's going to be 1 over t. Tau isn't it? Yeah. So 1 over tau. So that means that, let's see. One over tau is 416. Okay. Yeah. Sorry about that. This gets a little bit confusing sometimes. 67 t. And now we just got to simplify everything. So 416 times minus 3 times 15 is 250. Okay, so the final expression for VOT is going to be 200 plus 150, or 250 minus 150, which is 100, e to the minus t over tau, which is 416.67 t, and this whole expression is in volts. And yeah, one thing you can do if you want to check your answer when you're doing these is go back and plug in your initial conditions. If I set t to equal 0, then VOT equals 200. Which if we go back up, not that, we go back over here, it's going to be 200. And everything basically goes back to what it was in the steady states at the initial and final t's. So there you go. Not too bad. Just a little bit tricky because we're doing a different trick using the direct solution for the current instead of solving for the voltage or using the substitution like we did before. 7.41. This one is all symbolically done. We don't have any given values for these voltages, or rather these resistances and, I'll just say impedances and this current. And we're going to try and solve it anyway. So we want to find VOT as a function of IG R1 blah blah blah, and then explain what happens as the value for R2 gets larger. So first thing we need to do is find out the initial voltage for the inductor. And basically at steady states is going to be you have your steady state current, which is going to be IG. But as soon as the switch is thrown, IG is going to be going through that R2 resistor. Say IG is 0 minus, I guess, or is also going to be the same. So you can say that VL0 is going to be IG times R2. V equals I times R. The voltage drop across that resistor is proportional to the current flowing through it. So that'll give us our VL0. We also need to find the time constant of the circuit, so we need to find the equivalent resistance seen by the inductor after time equals 0. And these two resistors are in series. This is an open circuit from the current source having infinite internal resistance. So that's going to be REQ. So our circuit's going to simplify something like this. But since we've got kind of a tricky situation here, we can still find it the other way. But I think that it would be easier if we just look at the end behavior for this circuit, use our shortcut. Now, since there's no source, or rather there is a source still in the circuit, but the inductor is going to go short again. There's no resistors underneath it. We can say that VO infinity is going to be 0. So we can find that let's find tau real quickly. It's going to be L over R. And L is 80 millihenry. Or sorry, not 80 millihenry. I don't know why I did that. That's from the last problem. LAQ over RAQ. So that's going to be L over R1 plus R2. So VO of T is going to be 0 plus Y sub 0, so that's going to be IG R2 minus Y infinity, which is 0, e to the minus T over tau. This is going to be e to the R1 plus R2 over LT. And we'll say that is volts. So we want to find out what happens to VOT as R2 gets larger and larger. Well, VOT is going to increase here, but it will also decrease faster. So the initial value for VOT is going to be larger if R2 gets larger, but it will also decay faster because more energy is being lost in the resistor network after if the R2 gets bigger, then that's more resistance, more damping. The circuit reaches the steady state faster or slower. So we're going to go ahead and do the similar thing for V switch. So to do that, we're going to need to find out what the current through not V switch. We're going to need to find the current through that resistor R2. So we need to find the current through the inductor. And as we know before, that's IL0 IL0 was IG. Also gonna have to find out what the infinite current is. So the current at infinity, we look at our circuit again. Let's pretend that This switch is in here. So we got current going this way, current going this way. And this impedance is going to drop with time. Well, not really drop with time, but it's going to, the voltage drop is going to decrease. And that means we can do kind of like a current divider. Now, if you remember, in the current divider equation, you take like your opposite resistor that you want to look at the current through. So we want to find the current through R2. We're going to take R1, multiply it by the ratio of the two resistors, or divide by the ratio of the resistors, and multiply it by the source current, and that's going to be RI L infinity. So R1 over R1 plus R2 IG. Now if we use the same time constant we just came up with, L over R1 plus R2, gonna go ahead and plug in our values. So R1 plus R2 plus IG minus R1 plus R2. You actually cancel out the IGs, or not cancel out, but pull them out. And it's just going to be 1 minus R blah blah blah. But I'll leave it as is for now. So that's R1 plus R2 over LT. These are amps, and this is ILT. So we're going to need that to find out what V-switch is. Now V-switch, we're going to use Ohm's law again. ILT times R2. Now we can multiply everything out, but I'll just look at this expression and we'll be able to tell right away. So if R2 goes up, V-switch is going to go up. And it'll also decay slower, because but the current will also be a little bit less. So it's kind of like a balancing act. If V-switch is higher, then it'll take longer for the inductor to discharge, or not to discharge, to reach the steady state. It's not actually, well, it is discharging, but also not at the same time. It's changing states, basically. So we can say that if R2 goes up, then it's going to tend more and more down, but also slower. So hopefully that's not too confusing, especially since it's all symbolic, but let's go on to the next one. This problem is a little bit more complicated than the last one. The big thing is, well, I don't want to say it's more complicated. I want to say it looks more complicated. What we're going to do is we're going to analyze the circuit, and at both of the steady states, the steady state just before the switch is thrown and after a long time. So we're going to find I initial and I infinity, and then we're going to find the time constant tau by calculating the equivalent resistance. So basically we're going to analyze the circuit twice and then use that last bit to find how it responds. So this one's a little bit messy because there's this resistor and this voltage in the middle, V2. But as long as we are only looking for V1, which is the only one we really care about for now, then we can go ahead and combine the two resistors. And we'll use our KCL and our equations we always do, with one little caveat. V phi is going to be the opposite polarity, so to speak, because the plus is over here. So this will actually be minus I1 times, well, but we'll get to that in a moment. So I'll go ahead and write out I1. I'm going to combine the two resistors, so it'll be 480 minus V1 over 21 plus, or rather not plus, well, it can be plus. I'll just leave it as plus for now. Plus 4/5, which is 0.8, and then minus I1, so we're going to have minus 480 minus V1 over 21 equals V1 over 15. So I'm going to take the minus out, and I'll make this into basically 1 minus 4/5. So it'll be 480 minus V1 over 21 times, or not 25, 21 times 5 equals V1 over 15. So multiply everything here. 21 times 5 is 105. 105 divided by 15, 7. So 480 minus V1 equals 7 V1. So 480 divided by 8 is 60. So we can use that to find IO0 minus, which is also going to be IO0 plus. So that's going to be 60 volts divided by 15 ohms, or 4 amps. Now the next one, we have to introduce the 5 ohm resistor and the 280 volts. This is going to become a little bit more messy. So I'm going to go ahead and say 480 minus V2. This time we can't really combine them. Minus over 20 plus I3, which is 280 minus V2 over 5 equals V2 minus V1 over 1. I'll multiply everything here by 20. So that's going to be 480 minus V2 plus, what's 4 times 280? 1120 minus 4V2 equals 20 V2 minus 20 V1. So I'm going to simplify this expression. Say it's minus 20 V1 plus 25 V2 equals 1600. So it's going to become equation 1. Come on. Come on, pen, please work. So that's going to become equation 1. We're going to use the other KCL to come up with, I already wrote it down, but it's basically the same process. It's going to be minus 20 V1 plus 15 V2 equals 0. This is just using the other KCL. I just don't want to write it all out again. So I'll put that in my calculator. I get V1 equals 120 and V2 equals 160. So if we want to find IO infinity, it's going to be V1 divided by 15. So 120 divided by 15 is 8 amps. So that is our final current. Now, this may seem a little bit confusing because I didn't use the differential equation, but we don't really need to because we're only looking for the current anyway. So we just basically analyzing to, like I said, DC steady states. So this one is at time equals infinity. In reality, you can say time equals 5 time constants, because that's about how long it takes to reach the steady state with an RC/RL circuit. But we don't know tau right now, so we'll find out. And finally, we're going to find the equivalent resistance. So to make things a little bit easier, I decided to pull out this resistor and just do it, because it still works either way. We're basically just taking this little RL network and putting it onto this. The reason why I did that is because it's a little bit easier to find the R equivalent of the whole thing without this 15 ohms at the bottom. And the 15 ohms is just going to be in series, so we can add it back to find REQ. So I should say this is REQ prime. And REQ is going to end up being 15 plus REQ prime. Anyway, so we've got a pretty simple network right here. And we're going to apply a test source since there's no independent sources. I'm going to use 5 volts just because the resistors add up to 5. It's going to make the number a little cleaner. So that means V phi is going to still be the same as it was defined earlier. We're going to use a voltage divider for that. This is going to be 5, or whatever Vt is. I chose 5 divided by 1/5, or divided by times 1/5. That equals 1 amp. Or not 1 amp, 1 volt. So if V phi is 1 volt, 0.8 times V phi is 0.8 amps. So we can find the I, which is our test current. IR is going to be Vt over 5, so 5 divided by 5 is 1. 1 minus 0.8 equals 0.2. So REQ prime is 5 volts, our test voltage, divided by test current. So that's going to be multiplied times 5, so 25 ohms. So REQ for the whole network is going to be 15 from that RL plus the 25. So 40 ohms is the R equivalent. The time constant is going to be L over R, EQ. And I believe L is 80 millihenry. Yes, 80 millihenry. Divided by 25, or not 25. Divided by 40 ohms. This is going to be 40 milliseconds, which I believe is 1 over 250. Let me see. 40 minus 3. 25. Okay. So tau is 1 over 25 seconds. Alright. So to find our current, let me go ahead and pull it down just so I don't have to write it again. Where are you? The current as a function of time is going to be this. Please don't blank out on me. Okay. So I infinity we determined as 8, and I0 was 4. So we're going to have 8 plus, let's see, I0 minus infinity, so it's going to be minus 4. Minus 4 e to the minus t over tau, so 25 t amperes. Okay, so It's just a little bit of DC analysis trickery. I didn't write this out, but it's not too hard. We've done very, very, very many DC analysis problems by now, so I hope it's not too confusing. Alright, so this one is another one that looks pretty complicated, but it's not as bad as it looks. This thing might be a little bit confusing, that VO, because it shows the plus over here, but VO is just the voltage at the top here with reference to this bottom part here. So it's the same on at both times, at time 0 and time plus. So first thing we're going to do is we're going to find the equivalent inductance of these two inductors in parallel. It'll make the math a lot easier. So it's just like resistors. We're going to do 1 over 60 plus 1 over 40. I'm not worried about the order of magnitude because they are the same, so it'll wash out in the end. So 1 over 60 plus 1 over 40 is 24 millihenry. So now we're going to find out the initial and final current for that equivalent inductor, which I wrote a little equation right here for. We'll go back to these later whenever we need to find out I1 and I2t, but it's easier to find the voltage using an equivalent inductor. So at a steady state, it's going to be short, which means all the current is going to flow through it. So we can say that IL0 equals 25 milliamps, and IL infinity, by the same reasoning, will be 50 milliamps. Well, I should actually say it's minus, because even though I didn't draw it this way, we still have defined it the same way. So I will say minus. Okay, so now we need to find the equivalent resistance for the inductor after time equals 0. So there's a current source right here that's going to be open because it has infinite internal resistance. So that's just going to be REQ is 120 ohms. So LEQ is 24 millihenry divided by 120 ohms. Let's find tau. 24 minus 3 divided by 120 is 1 over 5,000. So now I'm going to go ahead and put all of this stuff together. So to do this, we're going to use IL infinity, which was minus 50 milliamps, and IL0, which was 25. So 25 minus 50 is 75. So plus 75 e to the minus t over tau, so minus 5,000 t. I'm going to leave it in milliamps because I don't want to write the order of magnitude. But it would also be 0.05 blah blah blah. You're going to get what I mean. So now we're going to take the derivative of this whole thing and multiply by the equivalent inductance to find the VO. So 24 minus 3 times the I of this thing. So derivative of a constant is going to be 0. And that's going to be 5,000. So I'll just say minus 5,000. 75 e to the minus 5,000 t. So let's think. Oh, yeah. Almost forgot. This is why you gotta be careful sometimes with the order of the magnitude. That's 75 milliamps, e to the minus 5,000 t. So this is going to simplify to 24 times 75 divided by 1,000,000 times 1,000 is 9. So it's going to be minus 9 e to the minus 5,000 t volts. So that's VOT. And now we're going to use a trick we learned in DC analysis with current division. Now, they're not resistors, the inductors, but they do kind of split the current the same way. Their impedances will split the current the same way. Now, their impedance varies with frequency, etc., but I won't get into that just because that's a course future topic for the course. We'll see that later. But anyway, we're just going to do kind of like you do before, where you want to find the current through a resistor. Say you have a resistor R2 and you want to find the current through that resistor. You're going to put the opposite resistor in the network on top. So we're going to do that kind of thing with the inductor. So we're going to take ILT and we're going to multiply by this ratio. So since I1 is through the 60 millihenry one, we want 40 millihenry on top. I'm not going to worry about the order of magnitude because, like I said, it's going to kind of wash out. The ratio is what's important. 40 plus 60. That's going to be 40% of IO. So what is 40% of IO? Let's see, 50 times 0.4 is 20. So minus 20 plus 0.4 times 75 is 30. And we're not going to worry about the exponent because it won't be changed. Milliamps. So we're going to do the same thing for I2T. Got to do our current division again. Use the opposite one. And we could also say that since I1 plus I2 equals IL, we could do subtraction. That would also work. But let's see. What's 60% of 50? That's minus 30. And I'll just do the other one in my head because it's 75 minus 30 is 45. So 45 e to the minus 5,000 t milliamps. Alright, so that was the last problem of this homework. This one I think is among the more tricky homeworks we have in this course. I hope that I was able to help you follow along the whole way. Some of the stuff we do is a little unorthodox, I know. But if you remember your first principles and you don't make silly mistakes, then you'll go pretty far.